What is a mixed model ANOVA? What are the hypotheses and assumptions? And how to interpret the results of a mixed model ANOVA? This is what we discuss in this video. Let's start with the first question. What is a mixed model ANOVA? A mixed model ANOVA is a statistical method used to analyze data that involves both between subject factors and within subject factors. But what are between subject factors and within subject factors? Let's look at an example. Let's say we want to test whether different diets have an effect on cholesterol levels. We would like to compare the three diets A, B, and C. So the factor diet has the three levels A, B, and C. To test whether there is a difference between the diets, we are conducting a study with 18 participants. The individual participants are called subjects. Now we randomly assign 6 participants to each of the 3 groups. Each participant or subject is assigned to only one group. In this case, we have a between subjects factor. Different subjects are exposed to different levels of a factor. In this analysis, our objective is to determine whether significant differences exist in the mean cholesterol levels among the various groups under study. And this is exactly what a one-way ANOVA does. Now, of course, we could also examine the impact of one diet across multiple time points. We could measure the cholesterol levels at each participant at the start of the diet, after 2 weeks and after 4 weeks. So the factor time has the 3 levels start, 2 weeks and 4 weeks. And in this case, the same subjects are being exposed to all levels of the factor. And this is called a within subjects factor. The same subjects are exposed to all levels or conditions. In this case, we want to know if there is a difference in the mean value of the cholesterol levels between the different points in time. And this is exactly what a repeated measures ANOVA does. Therefore, in a repeated measures ANOVA, we have within subject factors. So, in a between subjects design, each subject or participant is only assigned to one factor level, so that the different subjects only have the influence of the respective group. In contrast, in a within subjects design, the same subjects or participants are exposed to all factor levels, which enables a direct comparison of their reactions to each factor level. But what if we want to test if there is a difference between diet A, B, and C over the different points in time? So we want to test if there is a difference between the diets and if there is a difference between the different time points. Then we need a mixed model ANOVA because we have both, one between subject factor and one within subject factor. So in a mixed model ANOVA, we have at least one between subjects factor and at least one within subjects factor in the same analysis. Note, a mixed model ANOVA is also called a two-way ANOVA with repeated measures, because there are 2 factors and one of them results from repeated measures. Therefore, the mixed model ANOVA tests whether there is a difference between more than 2 samples which are divided at least between 2 factors. One of the factors is a result of measurement repetition. With the help of a mixed model ANOVA, you can now answer 3 things. First, whether the within subject factor has an effect on a dependent variable. Second, whether the between subject factor has an effect on a dependent variable. And third, whether there is a so-called interaction effect between the 2 factors. This gives us a good transition to the hypotheses. The first null hypothesis is the mean values of the different measurement times do not differ. There are no significant differences between the groups of the within subject factor. Then, of course, there is the second. The means of the different groups of the between subject factor do not differ. And the third null hypothesis reflects the interaction effect. One factor has no effect on the effect of the other factor. What are the assumptions of a mixed model ANOVA? Normality. The dependent variable should be approximately normally distributed within each group of the dependent variables. This assumption is especially important when the sample size is small. When a sample size is large, ANOVA is somewhat robust to violations of normality. Homogeneity of variances. The variances in each group should be equal. In mixed model ANOVA, this needs to be true for both the within subjects and between subjects factors. The Levene's test can be used to check this assumption. Homogeneity of covariances, sphericity. This applies to the within subjects factors and assumes that the variance of the differences between all combinations of the different groups are equal. What does that mean? Let's start with the differences between all combinations. To do this, we simply need to calculate the difference of the first group minus the second, the difference of the first group and the third group, and the difference of the second group and the third group. These calculated differences should now have the same variance. This assumption can be tested using Morshley's test of sphericity. When this assumption is violated, adjustments to the degrees of freedom, such as Greenhouse-Geiser or Heinfeld, can be used. Independence of observations. This assumes that the observations are independent of each other. This is a fundamental assumption in ANOVA and is usually assured by the study design. No significant outliers. Outliers can have a disproportionate effect on ANOVA, potentially causing misleading results. It's important to identify and address outliers. Let's calculate an example and I'll show you how to interpret the results. Let's say this is our data that we want to analyze. We want to know whether therapy A, B, and C and 3 different time points have an effect on cholesterol levels. Each row is one person. The therapy is the between subject factor and the time with the levels before the therapy, in the middle and at the end of the therapy is the within subject factor. So, the first patient on therapy A had a cholesterol level of 165 before therapy, a cholesterol level of 145 in the middle, and a cholesterol level of 140 at the end. Let's first calculate the example online with Data tab and then discuss how to interpret the results. To calculate an ANOVA online, simply go to datatab.net and copy your data into this table. You can also load this example dataset using the link in the video description. Then click on Hypothesis Testing. Under this tab, you will find a lot of hypothesis tests, and depending on which variable you click on, you will get an appropriate hypothesis test suggested. If you copy your data up here, the variables will appear down here. If the correct scale level is not automatically detected, you can simply change it under Variables view. For example, if we click on Before, Middle and End, a repeated measures ANOVA is automatically calculated. But we also want to include the therapy, so we just click on Therapy. Now we get a mixed model ANOVA. We can read the 3 null and the 3 alternative hypotheses here. Then we get the descriptive statistics output. And here we see the results of the analysis of variance and also the post hoc test. We'll look at these again in detail in a moment. But if you don't know exactly how to interpret the results, you can also click on Summary in Words. But now back to the results. Most important in this table are these 3 rows. With these 3 rows, you can check if the 3 null hypotheses we stated before are rejected or not. The first row tests your null hypothesis, whether cholesterol level changes over time, so whether the therapies have an effect on cholesterol level. The second row tests whether there is a difference between the respective therapy forms with respect to cholesterol level. And the last row checks if there is an interaction between the 2 factors. You can read the p-value in each case right at the back here. Let's say we set the significance level at 5%. If our calculated p-value is less than 0.05, then the respective null hypothesis is rejected. And if the calculated p-value is greater than 0.05, then the null hypothesis is not rejected. Thus, we see here that the p-value of before, middle and end is less than 0.05, and therefore the values at before, middle and end are significantly different in terms of cholesterol levels. The p-value in the second row is greater than 0.05, therefore the types of therapy have no significant influence on the cholesterol level. It is important to note that the mean value over the 3 time points is considered here. It could also be that in one therapy the blood pressure increases and in the other therapy the blood pressure decreases, but on average over the time points the blood pressure is the same. If this was the case, however, we would have an interaction between the therapies and the time. We test this with the last hypothesis. In this case, there is no significant interaction between therapy and time. So there is an influence over time, but it does not matter which therapy is used. The therapy has no significant influence. If one of the two factors has a significant influence, the following 2 tables show which of the combinations differ significantly. I hope you enjoyed the video and see you next time.